Let me show you how to calculate forces on springs. This is something called Hooke's law. And properly, there really is a minus sign on here. I'll talk about why that is. We're not going to go there so much, but this is the idea, is that if we stretch a spring, there's a force called a restoring force that will tend to want to make the spring whatever shape it was before. So if we stretch the spring, that force makes the spring try to be smaller, and if we compress it, it tries to make it bigger, right? There's a constant called the spring constant, right? And the bigger that is, the stiffer the spring, right? So the ones we have in our classroom are, say, 30 newtons to stretch it a meter, 30 newtons per meter. On your car, there are probably thousands, hundreds of thousands, maybe 1,000,000 newtons or something, who knows, right, to stretch that thing a meter. I mean, imagine that, right? And then x is the amount that, it's not the length of the spring, but it's how much it's been distorted, either stretched or compressed, right? So here's a spring, maybe this is its original length, right? And then maybe we stretch it. Well, that x is this distance here. That's the key concept. It's the length of the spring. It's not the length of the spring, but it's a change in length of the spring. Okay, here is why there's a minus sign, because if I stretch it this way, the x is actually this way. That's the way of x, right? It's really to the right, but the force the spring's exerting on me is to the left. So properly, there's a minus sign up there. I'm not so much going to worry about that. Okay, let's just do one example problem here, and then I'll throw the rest up here, right? Ali's above. Stretches a 53 Newton per meter spring, right? 13 centimeters with what force? Well, F equals kx, right? So that equals 53 newtons per meter. Literally, that means if we stretched it a meter, it would take 53 newtons, right? And then 13 centimeters is 0.13 meters. Got to have meters, right? And then 53 times 0.13 is 6.89, right? And then the units are, meters go the way of the bison, we end up with newtons. Yeah? So these things tend to have, if we graph this, right, force versus distance like this, they tend to be linear, just nice straight lines like that, okay? F equals kx plus 0. This is like y equals mx plus b, right? This is our y-intercept is 0. The slope of the line is k, and that's how you'd find the k, is actually graph a bunch of points and find the slope of it. So anyway, that's enough about springs. Oh, the final thing, actually not quite enough, right, is that this is a simple spring. There are springs that have all sorts of force curves. This is a linear spring. There are some, there are springs that, like, at first don't have much, then they get steeper, then they get steeper like that. You could, as an engineer, you could design pretty much any force curve you want into a spring. Some of the springs in our lab are ruined, and so they actually go like this. They're like I'll show you how that is, but it's kind of funny. Looks like a mistake, but anyway.